So here we are in lecture 9.6. We're going to talk about a very different kind of placement algorithm. We're going to talk about analytical methods. So all of the placement techniques that we've talked about up till now in this lecture have been based on some form of random improvement, random exchange, random perturbation with some interesting control parameters like, for example, simulated annealing. Those are really good and powerful techniques, but they really run out of steam. They are not very efficient when you get to, let's say, 500,000 gates. And since people are really placing things with a few million gates, 10 million gates these days is a kind of an atomic placement task, maybe even more, the annealing-like methods don't really work very efficiently. The analytical methods are based on a very different kind of an idea. We're actually going to write an equation, a mathematical equation, and we're actually going to use calculus on it and some interesting linear algebra, and we're going to solve that equation numerically. And the solution of that equation is going to be the placement of the gates. And if you're thinking, wow, if I have 1,000,000 gates, am I going to have an equation with like 1,000,000 x's and 1,000,000 y's in it, and you're telling me that I'm going to do calculus on it and I'm going to solve it? I'm going to tell you, yes, that's actually how modern placers really work. So let's start by talking about the sort of the introductory background to analytical placement.
We're going to write an equation whose minimum is the placement. Now you understand something about this because, roughly speaking, what the iterative improvement simulated annealing style placers did was iteratively minimize a wire length function whose value was determined by the locations of all the gates. But now we're going to write something that looks more like a physics equation, a continuous valued equation, an analytical equation, an equation that I can actually write down, and we're going to solve for its minimum. So if you have 1,000,000 gates, you need 1,000,000 x, y values. As a result, one for each of your 1,000,000 gates. We're going to formulate an appropriate cost function for all of the gate level x, y coordinates. That function is going to be a function of 1,000,000 x's and 1,000,000 y's. And then we're going to solve it analytically, which means we're actually going to do math on it. And we're going to get 1,000,000 x's and 1,000,000 y's. And that will be the minimum of this function. And the resulting set of values give you the placement of all 1,000,000 gates. And I recognize that this sounds kind of crazy, but it works great. And there's a trick. The trick is that you have to figure out a way to write the wire length in a mathematically friendly form that you can optimize. And what's interesting is that this is actually quite possible. And in fact, there's several different ways of doing it. All modern placers for big ASICs and big systems on chip are analytical in this style. So the big idea behind the class of analytical placers that we're going to study in this lecture is something called the quadratic wire length model. And the idea is that it turns out that by optimizing this thing called the quadratic wire length instead of the half perimeter wire length, it has the nice friendly mathematical properties we need to be able to derive a solution. So said differently, why do we pick the quadratic wire length? Because the mathematics works out in a way that we can solve. So for a 2-point net, this is actually very simple. This is the squared length of the distance between the points. So I've got a little grid here, the same grid I've been showing previously. X goes from 0 to 4, so there's 5 columns. Y goes from 0 to 5, so there's 6 rows. Let's assume that the coordinates refer to the center of the grid elements, and there's a gate at 1, 4 labeled 1 and a gate at 3, 1 labeled 2, and this is a 2-point net, as we know. What is the length of this net? It's just the length of this hypotenuse of this triangle. So I'm just going to sort of draw this kind of like a triangle. It's just the length of the straight line, the blue straight line between gate 1 and gate 2. And that's nothing more than x1 minus x2 squared plus y1 minus y2 squared. So that's actually pretty straightforward. And if we were to, actually calculate that, that's going to be 3 minus 1 squared plus 4 minus 1 squared. Do the math, and the length of this wire is 13. So this is straightforward. Note that there's no square roots here. Okay, this is the squared. I'm going to write this as S-Q-U-A-R-E-D, squared length here. Okay, it's the squared length between those two gates. So it's not as mathematically friendly if you take the square root. But perhaps more interestingly is what happens if your net has more than 2 points in it? That's not at all straightforward. So here is now a k-point net. K in this particular case is 4. So I again have the grid. X goes from 0 to 4, Y goes from 0 to 5, and there are 4 gates. Gate 1 is at 1, 4. Gate 2 is at 3, 1. Gate 3 is at 3, 3. And gate 4 is at 4, 5. And I've got a wire drawn here that's kind of the way a physical wire might get routed. But it's not at all clear what quadratic wire length means here. And so here's the recipe. The first thing you do is you replace the one real net with k times k minus 1 over 2 2-point nets. And the way to think of that is that I'm just going to add a new net between every pair of points. And that's how many pairs of points there are. Right? So this has a name. It's called a fully connected clique model. This is pronounced clique model. And so the way this one would work is I'm showing again the grid without any wires in it on the right here, gates at 1, 4, 3, 1, 3, 3, and 4, 5. And what I'm just showing is that if k is equal to 4, then 4 times 4 minus 1 over 2 is 6. And so what's going to happen is there's 1 2-point wire, 2 2-point wires, 3 2-point wires, 4 2-point wires, 5 2-point wires, 6 2-point wires. I'm just drawing every wire in. K times k minus 1 over 2 for k is 4. It's 4 times 3 over 2. There are 6 2-point nets that we're going to connect. So that's what you do. You take the one multi-point net when k is greater than 2, and you turn it into k times k minus 1 over 2 2-point nets. It has a name. Sometimes it's called fully connected because obviously every pair of gates has a wire connecting it. More commonly, it's called a clique. So here's that same example. I'm showing the clique model again. The grid, x goes from 0 to 4, y goes from 0 to 5, gates at 1, 4, 3, 1, 3, 3, and 4, 5, and I'm showing all 6 2-point nets. The other thing you got to do is that you have to weight, which is to say multiply the length of each of these quadratic wire lengths by a number. So let's just think about it. You know, I used to have one physical net, and I replaced this one physical net with 6 nets, and I'm going to measure the quadratic wire length of each of those 6 nets. It makes some sense that I need to multiply by some small number so that I don't dramatically overestimate how much wire this physical net needs. And so there are lots of ways that people do this, but the traditional weighting factor is 1 divided by k minus 1. So in this particular example, if we were to estimate the wire length, there would be 6 quadratic wire lengths, which are squares of differences of coordinates, and each one of them is multiplied in this case by 1 over 4 minus 1, which is 1/3. So this is 1/3 times 4 minus 1 squared plus 5 minus 4 squared, plus 1/3 times 4 minus 3 squared plus 5 minus 1 squared, 1/3 3 minus 1 squared plus 4 minus 1 squared, 1/3 3 minus 1 squared plus 4 minus 3 squared, 1/3 4 minus 3 squared plus 5 minus 3 squared, 1/3 3 minus 3 squared plus 3 minus 1 squared. 6 2-point quadratic wire lengths, each multiplied by this weighting that sort of reduces their estimated length. Now the other thing I'll notice here is that when k equals 2, this weight is just 1 divided by 2 minus 1, which is 1, so there's no special treatment for the 2-point case. Right, so it all works out. You always multiply by the weighting factor 1 over k minus 1, and when it's a 2-point net, nothing special happens. You just multiply it by 1. So there's one more big idea here, kind of an interesting idea. To make the math work out easily, we're going to ignore the physical size of all the gates. We're going to pretend the gates are dimensionless points. Now, previously in the iterative improvement placer, we also sort of ignored their size. We pretended they were all the same size, but it's not like we actually said they had no size at all. We just assumed they were as big as the square on the grid. We are now going to honestly pretend that they don't have any size at all. They are dimensionless. And the big thing is we're going to ignore the fact that the gates can't go on top of each other. And as we shall shortly see, the technique we're about to develop puts lots of gates on top of each other. It's going to be the second part of our algorithm, is how we fix that. This sounds strange, but it allows us to write a very simple, very elegant equation for the placement and then to solve it quickly and effectively. So why do we do these interesting mathematical tricks? Why do we model the wire length as a bunch of fractionally weighted two-point quadratic forms? And the answer is because the math makes it possible for us to solve. So the easiest way to see this is with a little example. So I've got a little example here. So I'm modeling the chip as a box. X goes from 0 to 1 and Y goes from 0 to 1. This is totally arbitrary, by the way. This could go from 0 to 1, it could go from 0 to 100, it could be in microns, doesn't matter. The math will work out. And there are two gate points. They have indexes 1 and 2. They are the green circles with 1 and 2 next to them. And there are three nets. They're each 2 points to just keep things small and simple. And they have weights 1, 2, and 4 respectively. And there are two pads. And I'm just putting a little arrow to the pads. There are two pads. There's a pad at 0, 0, it's the red square, and a pad at 1, 0.5. The pads are fixed pins. Those are the things, if you will, around the edges of the chip that are the IOs, the input-outputs. And so there are three wires. There's a wire from the pad at 0, 0 to gate 1 with weight 1, a wire from gate 1 to 2 with weight 2, and a wire from gate 2 to pad 1, 0.5 with weight 4. And I'm just making the weights up so you can see what happens when we do the math, and the math all turns out nice. So it's very easy to write the quadratic wire length. And that, in fact, it's one of the reasons we do it like this. So if we just look at the problem, the first thing we see is I'm going to look at the wire length from gate 2 to the pad at 1, 0.5. That's 4, the length, the weight on the wire times x2 minus x1 squared plus 4 times y2 minus 0.5 squared. Where are those constants? Well, the pad is fixed at 1, 0.5. So, we subtract 1 from x and square it. We subtract 1.5 from y and square it. And the fractional multiplier, or in this case, the weight multiplier, it's not a fraction, is a 4. The other wire that connects gates 1 and 2 has a weight 2, so you get 2 x2 minus x1 squared plus 2 y2 minus y1 squared. The final wire has weight 1, and it connects to a pad, 1 times x1 minus 0 squared plus 1 times y1 minus 0 squared. That's the components of the quadratic wire length. You add these all together, and that's it. This is really as simple as that. Now there's one other thing I'll have you notice, and this turns out to be very important. If you look at these terms, there are no terms where there's an x variable multiplied by a y variable. In each one of these cases, we get terms that look like xi squared and xi times xj, or yi squared, yi times yj. Right, so if you look at the middle equation, right, you're going to get an x2 squared, an x2 x1, and an x1 squared. You're going to get a y2 squared, a y2 y1, and a y1 squared with some constants. And also for the wires that connect to pads, you're just going to get linear terms, x2s and x2 squareds, y2s and y2 squareds, for example, on the first one. But you're never going to see an x multiplying by a y. This turns out to be extremely important because it means I can separate the x terms and the y terms, and as we shall see, I can actually optimize them separately. So the next great question is, how do I optimize this? So let's go look.